Hi again. So I know most everyone is familiar with Albert Einstein's famous equation E equals mc squared, which relates energy and mass to one another. But do you know what he won the Nobel Prize for? Believe it or not, it wasn't for his revolutionary work on the theory of relativity, but instead was for his explanation of the photoelectric effect. The photoelectric effect, simply stated, is that many metals eject electrons when light is shined on them. Now, this phenomenon was well known before Einstein began working on it. The problem was in understanding the mechanism which governed it. One experimental observation which baffled scientists was that the effect was independent of the brightness of the light used or the duration of the illumination. Light with long wavelengths were unable to dislodge electrons from the metal surfaces regardless of how long the lights were shined or how bright the rays were. The key lies in quantum mechanics. Don't worry, it's not that complicated. You see, photons, the elementary particle of light, comes in discrete quantized energy units, and that the energetic barrier for emitting electrons from metal surfaces lay in using light with high energy quantum units, which is not dependent on the amount or intensity of photons used. You see, light with long wavelengths, such as red and infrared light, are composed of lower energy photons than light with shorter wavelengths, such as blue and ultraviolet. Mathematically, this is defined as the Planck-Einstein relation, E equals hc over lambda, where c is the speed of light, lambda is the wavelength of light being considered, and h is Planck's constant, named after Max Planck, another prominent physicist of the same time period as Einstein. This phenomenon of the photoelectric effect can be visualized through the following experiment. Holiday tinsel is affixed to a conductive wire, which is taped to a metal surface, in this case an aluminum pie tin. A plastic rod is charged with negative electrons which it passes to the tinsel. See how this makes the tinsel repel itself, as light charges repel. Now, to abolish the repulsion, all we must do is shine light on the metal, as so. Nothing's happening. Let's turn up the intensity. Still nothing. But wait, if we remember, it's the wavelength that matters, not the intensity. Let's see what happens when we use a black light in the UV range. There it is. You see, what is happening is that as electrons are being ejected from the pie tin by the light, this allows space for the excess electrons in the tinsel to travel to the pie tin, which completely dissipates the repulsion observed. And there's quantum mechanics for you. Now, this effect has immense relevancy in photovoltaic applications, such as solar cell energy capture, a field which has the potential to totally resolve the present energy crisis we're facing as a global community. There's obviously much work to be done in that area, but we're certainly getting closer to finding the answer. That's it for us. I'm Justin Scott, your Transit TV Science Genie, reminding you to always ask questions.